we will continue where we have left last class, and we were talking about glass formation. We basically talked about the T naught concept. T naught concept basically gives two things. One, what is called extension of solid solubility. As you can see, if you choose any composition, for example, if I redraw this T naught and choose a composition of this sort and can bring the liquid below the T naught in such a way that I take care of even the temperature raise during recalescence also, that if I can undercool the liquid sufficiently so that it can undergo what is called partitionless solidification, then I have an alloy here which has the same composition as the liquid that with which I have started, and this is a single phase solid solution now. So I have a single phase solid solution which has much higher solute content than it can actually contain according to the phase diagram. So that means basically what I have done is I have got an extended solid solution. So this is the most crucial aspect of the T naught concept, and that is what you get whenever you undercool. So undercooling can give you variety of things. One thing that we have seen earlier in the beginning itself, that undercooling can lead to a higher nucleation rate and can give you finer grain sizes. So fine grain size that we usually see at faster cooling rates is basically coming from higher undercooling. But yesterday, if you remember, we talked about it, this particular undercooling and higher nucleation rate, we are only concerned with the upper part of the C curve. When we actually come to the C curve later, we will look into it, and if you are below that, then basically this concept that higher undercooling leading to higher nucleation rate is actually not right, because it is below the the half part of the C curve, the bottom half part of the C curve, it is a diffusion which takes control, and as a result, just because you have a higher undercooling does not mean that you will have higher nucleation rate. So basically, as that top portion of the C curve is concerned, then we are right, we can say that the higher faster cooling rate or higher undercooling will give you fine grain sizes, but that has nothing to do with the T naught concept. Just higher undercooling leading to a higher nucleation rate, and as a result finer grain size. And the T naught concept basically tells us that yes, we can get extended solid solutions, and if you can choose your composition as an appropriate composition, you may end up in getting a glass, provided, for example, if you have two T naught curves like this, and if you are choosing an alloy composition, and in fact we call this range as the glass forming composition range, wherever the two T naught curves intersect the Tg line. More or less Tg is not a strong function of the composition of the alloy in any system. So as a result, you see it more or less as a horizontal, and so wherever the two T naughts intersect that Tg, that range will give you the range of compositions where liquid is more stable and liquid has no chance to undergo partitionless solidification. As a result, this liquid, once it reaches the Tg, will undergo glass formation. So that is why we call this as glass forming composition range. But all this you have to keep it in mind is only we are talking from the thermodynamics point of view. In principle, you can even have a larger glass forming composition range if you have used a much faster cooling rates, that kinetics takes over, that you are somehow preventing the crystal to form. Ultimately a glass will form whenever a crystal is suppressed. So if you can suppress the crystal formation from the liquid, you can always get a glass. So but this gives you a tentatively, so by just looking at the phase diagram, we will be able to tell which phase diagram has a higher glass forming ability, which does not, provided I can plot the T naughts. And I have also mentioned to you some time back, we will also talk about it when we continue with glass formation, what is glass forming criteria? One of the glass forming criterion involves the phase diagram itself. How deep is the eutectic or how shallow is the eutectic? So that you can see from the phase diagram itself, and we have talked about it, a criterion based on that what is called the deep eutectic criterion. We will come to it as we go along. So this glass formation is the second concept that you get from the T naught, and yesterday in the last class we started talking about it, and we looked at how the glass forms as one of the parameters, which is the viscosity. We looked at how viscosity changes with temperature, and we said there is a particular temperature at which the viscosity of the liquid reaches almost that of 10 to the power 13 or 14, and that particular temperature defines what is called the Tg, because below that temperature liquid cannot be undercooled, because by that time the atomic movements in the liquid freeze, and as a result this liquid becomes a glass. Now let us try to understand this glass formation from the thermodynamic point of view, and what we have seen viscosity is mostly like a kinetic point of view, and look at it from the thermodynamics. How do we understand glass formation? Glass formation we understand from the entropy criterion. If I look at how the entropy changes as a function of temperature, we all know that the entropy of a liquid is higher than the entropy of the solid, am I right? So S of liquid is always higher than S of solid, but at the same time we also know that the rate at which the entropy of liquid changes with temperature is also higher than the rate at which the entropy of solid changes with temperature. Why? Because we know pretty well that S is nothing but integral Cp dt by T, and as a result the ds by dt I can always write as Cp by T, and because of this, and because we know that Cp of liquid is always higher than the Cp of the solid, so I can expect the slope of the entropy versus temperature curve to be steeper for the liquid when compared to the solid. This is understood. If that is the case, if I plot entropy versus temperature for any metal, for example, I can show that the entropy changes something like this. Of course there is a mistake in this curve. What is it? These are not straight lines. These two portions which I showed them as straight lines are actually not straight lines. If I say that they are straight lines, basically I am saying that the slope is constant. The slope is constant means Cp by T is constant. Cp by T is not constant, it varies with temperature. So as a result, in principle, that these two portions, this portion and that portion, are actually not straight lines. One has to remember that. But for the present understanding we do not need to bother about that much, but what we need to understand is that this slope is higher than this slope. If that is the case, and what is this, that at the melting point in principle at the Tm there is something called delta SF, what is called entropy of fusion, isn't it? So in fact entropy of fusion is known to be delta SF is actually delta HF by TF, because ds is actually dH by T. If you look at the second law of thermodynamics, the basic definition of entropy, where ds is dH by T, so you can always write that delta SF is nothing but delta HF. So if I know the heat of fusion and if I know the melting point, in principle I can find out what is the entropy of fusion, okay, and this quantity is basically this quantity. So once I know that, now let us look at the nature of the two curves on the liquid side and on the solid side. Because the slopes are different, if I now undercool the liquid below the melting point, that means the liquid remains as liquid below the melting point and its entropy can be treated as nothing but an extrapolation of this curve. So, if I know what is the, if I want to know what is the entropy of the liquid at some temperature below the Tm, I simply basically extrapolate this and say that at a particular temperature here the entropy of liquid is this, if it remains as liquid, am I right. So, if I keep extrapolating that to a very low temperatures, I will come to a situation where at some particular temperature suddenly I start seeing that below that particular temperature the entropy of the liquid becomes lower than the entropy of the solid, which is an absurd, isn't it. It is like a paradox, and this particular paradox is what people call it as Kauzmann paradox. It was Kauzmann in around 1950s, possibly 1954, who pointed out at this paradox. He says there is a temperature below which the entropy of the liquid actually appears to be below that of the entropy of the solid as it keeps on undercooling, and that particular temperature at which you see this happening will be the temperature where liquid wants to avoid that kind of a paradoxical situation, and the only way it can avoid is to simply become a glass, and that is what we call it as the ideal glass transition temperature. The thermodynamic definition of a glass transition is that where the liquid freezes into some structure, some solid structure, in order to just avoid becoming a crystal of having a situation of lower entropy than that of the solid. So, just to avoid this particular paradoxical situation, liquid becomes a glass, and that particular temperature is what we call it as the glass transition temperature. So, this is a thermodynamic definition of the glass transition temperature, and in principle we can even calculate this glass transition temperature very easily. How do you calculate the glass transition temperature? Basically find out the temperature at which delta S is 0. Okay. So, the definition of a glass transition is delta S is 0, delta S between the solid and the liquid. So, calculate the entropy of the solid using this, calculate the entropy of the liquid using that, accepting that in one case Cp of solid you will use, in another case you will use Cp of the liquid, and once you know this, to find out that particular temperature where this entropy of the liquid becomes equivalent to the entropy of the solid, and that is the temperature where you can say one can call it as Kauzmann temperature. People also call this Tg as Tk, Kauzmann temperature, or the glass transition temperature, ideal glass transition temperature. And so, this is how one can in principle calculate what is this glass transition temperature, and theoretically in a number of cases, if you are just simply looking at pure metals, this temperature is actually very close to absolute 0. That is the reason why most of the pure metals you do not see that they become glasses, but in case of alloys, yes, you will see that it is easier to become a glass in case of alloys, because in case of alloys the entropy is still higher because of the configurational entropy being added in the liquid. So, as a result it is, the curve is much steeper. So, as a result when you see that the temperature at which this intersects that of the solid is higher. For example, if you imagine that this is steeper, you would see that it intersects somewhere here. So, that means the actual Tg is higher. So, you will see in that is the reason why you will see most of the bulk metallic glasses which are very stable glasses, their glass transition temperatures are actually higher. So, because they form glasses very easily, and you would also, there are a number of parameters to look into that, we will see it as we go along. So, this is one of the very important concept which comes from thermodynamics, but if you look at this particular thing a little more carefully, what you see is that there is a situation whenever a glass is being formed, the delta S is 0, and what about delta G? What about delta G? delta G for any phase transformation in principle has to be 0, otherwise there is no phase transformation. If you treat liquid and glass as two different phases, at any given phase transformation delta G is 0, is not it. So, if that is the case, if delta S and delta G are 0 in principle, obviously delta H is also 0. Okay. So, that is a very special transformation. In fact, this is what we call it as a second order transition. Have you ever come across first order and second order transitions? Anybody who has heard what is a first order transformation? First order involves latent heat, second order does not involve latent heat. Anybody? Yes, you are partly right. First order transition involves a latent heat of fusion. Okay. That means that there is a certain delta H associated with the first order transition, whereas the second order transition is the one where there is no delta H associated with it. That means there is a transition, but there is no delta H associated. For example, if you draw, if you take a sample, let us say a metal like this, an aluminum, and keep heating it in a DSC, how do you recognize it is melting in a DSC? Endo peak you will see. Okay. You will see an endo peak, am I right? A solid, when it becomes liquid, obviously it absorbs heat at a particular temperature. So, you see a peak corresponding to this melting, and the area under the peak actually is what is the delta is related to, of course, with some scaling factor, is related to the delta H of fusion. So, any melting transformation or any transformation, for example, even a simple example transformation such as a BCC iron changing to an FCC iron, or an FCC iron changing to a BCC iron, all these transitions, they all will have a delta H associated with it, and we can easily see them. Only thing is, solid solid transformations will have a smaller delta H, solid to liquid transformations will have a larger delta H, because the two phases have largely different enthalpies, and as a result the delta H is larger. Similarly, when a solid is actually becoming a gas by a sublimation, you will see the delta H is much larger, because the enthalpy of the gas is much different from the enthalpy of the solid. So, the enthalpy difference actually is related to how much is the change in the structure that is taking place from one to the other. Particularly if it is simply a FCC to BCC transformation, the delta H is usually very small. So, this is how we can see the delta H, whereas in a second order transition you will not see this happening. That is why, for example, if I take a glass and simply heat a glass in a DSC, what we usually see is that if I heat a glass, I see a plot like this, where here is temperature, where here is some delta H, heat evolved or heat absorbed, whatever it is, depending on the direction. So, you see as I heat, you see a step somewhere here, and then you see a peak. What does this step and what does that peak correspond to? Yes, the first one is what is called the glass transition, called Tg, and the second one, where here at this point you start seeing a peak, we call it as onset of crystallization. Then what is happening at the glass transition? When I am heating a glass, at the glass transition, what is actually happening? And what is that is becoming a crystal later? That means between this Tg and this, if I call it as Tx, what exists between the two temperatures? What is it? Something is, see, we say, when I say glass transition, that means glass is changing into something, and that something is crystallizing at Tx. What is it changing it to? If you remember, what has changed it to glass in the previous plot that we have drawn, previous curve that we have drawn, where you see the entropy. So, this is what is Tg. What is it above the Tg? It is liquid, it is a supercooled liquid. It is a supercooled liquid which is transforming into a glass at Tg. So, when I start heating the glass, this glass will again transform to a supercooled liquid. It will transform to a supercooled liquid above this temperature when I start heating the glass, and this supercooled liquid, because it is not stable, it is much below its normal melting point, and because that liquid is not stable, it starts transforming into a crystal. Depending on whichever crystal can easily nucleate, it can nucleate to some crystal, and that is what we call it as a crystallization. So, what you have here between these two is a supercooled liquid. In fact, that the temperature difference between the Tx and Tg is one of the measures of how strong is a glass. The larger this difference, which we call it as delta Tx, which is equivalent to Tx minus Tg. This delta Tx is one of the measures of how stable the glass is. That means the glass does not want to crystallize. In fact, all what are called silicate glasses, they do not want to easily crystallize. You will see a large difference between Tg and Dx. Similarly, all bulk metallic glasses are all like that, that they can become a supercooled liquid, and they do not want to become because the viscosity of the liquid, the atomic movement in the liquid is so difficult. Imagine a bulk metallic glass with some 6 elements in it. The atomic movements, the diffusion is so difficult. So, these atoms which are present in this liquid do not want to crystallize to form a unit cell. So, formation of a nucleus and its growth is so difficult in such liquids. As a result, they remain as liquid for a longer time or a higher temperature. That is the reason why you see this difference can be as high as about 100 Kelvin. Most of the bulk metallic glasses have a large delta Tx, this is one of them. So, we can easily see whether the glass is a stable glass or not based on this. So, but what is more important for us for the discussion at the moment is see that you see a step there. The moment you see a step there, that means it does not it is not associated with any delta H. You do not see either an exothermic peak or an endothermic peak there. So, you will only see a step, and that step indicates that the delta H is 0, and if the delta H is 0, then what is that is happening, what is the change that takes place there. To understand that, we need to understand what is the meaning of first order and second order. Let us look at that. We call something as a first order transition when the first differential of the free energy is discontinuous at the transformation temperature. What do I mean by first differential of free energy? If you look at free energy and look at dG is VdP minus SdT, if I write this Maxwell's equation. So, the first differential of free energy with respect to temperature at constant pressure is minus S. Am I right? Similarly, the first differential of free energy with respect to pressure at constant temperature is nothing but V. So, these two will be discontinuous at the transformation temperature. That means, if I plot S versus T, you will see a situation like this. At the transformation temperature, there is a discontinuity between the entropy of the liquid and the entropy of the solid. I mean, I am talking of liquid solid as a transformation. Any transformation you take, product and the parent phase. So, between the product and the parent phase, there will be an entropy difference. But if I plot the G versus T, G versus T, you do not see such a discontinuity. For example, if I plot You remember this plot we have already done. We say that this is the liquid portion and this is the liquid free energy curve and this is the solid free energy curve. And if I want to see what is the stable states beyond this temperature, it is the liquid that is stable, below this temperature it is the solid that is stable. So if I look at the free energy of the stable states, you see that this is the free energy of the stable state below the melting point, this is the free energy of the stable state above the melting point. So if I simply look at the free energy curves of the two stable states and at the transformation temperature, there is no discontinuity there, there is only a change in the slope. So you will see the curve is continuous, curve is actually continuous, excepting that at the transformation temperature the slope of this and slope of this are different, and the slope actually is this, is entropy. That is the reason why you will see at the transformation temperature there is a step, because there is a slope change here. The step that you see here is because of that slope change. So you can see the first differential of the free energy itself is continuous at the transformation temperature, but the first differential of the free energy is discontinuous. And similarly, because if S is discontinuous, because S is related to H is H by T, so H also becomes discontinuous. That is the reason why if I plot H versus T, I will again see this same discontinuity. So because entropy is discontinuous, automatically enthalpy becomes discontinuous. And similarly, if I plot V versus T, you will also see a discontinuity of V versus T, something like what we have seen just for the S. I can say V H V also at the transformation temperature, you will see suddenly it is discontinuous. That is the reason why we always talk about a volume expansion or volume contraction during the solidification. Why is that? Because the volume of the liquid is different from the volume of the solid at the transformation temperature. This volume can change with temperature, because we talk about volume expansion. So there is a volume expansion that can occur in the solid state, there is a volume expansion that can occur in the liquid state, but at the transformation temperature, if I look at it, there is a difference in the volume, and that is why we talk about shrinkage during in a foundry. For example, we talk about shrinkage elements, all that. So this is all because of this. So if I plot S, H, V, all three of them have discontinuity. So those are all the first differentials. Now if I say a second order transition, second order transition is that transition where the first differential is continuous while the second differential becomes discontinuous. That means what? That means the first differential is continuous, that means H, S and V, all of them are continuous. That means delta H should be 0 for the transformation, delta S should be 0 for the transformation, delta V should be 0 for the transformation. In fact, this last one is a very important property which people are using in bulk metallic glasses to make any shapes that you want. People are making what are called micro gears, the world's smallest gear. If you can go to the Google and see, which is of the order of 100 microns size, has been made by bulk metallic glass. The basic reason is that the delta V is 0. Once the delta V is 0, when a liquid is transforming into a glass, there is no volume expansion or volume contraction. So as a result, there is no actually the shrinkage or the expansion that we talk about. So whatever is the mold that you create, exactly the liquid will fit into that. So what if you can create a small mold by whatever means that you want, for example lithography you can use, there are variety of techniques that are available nowadays to make very small molds, and you put liquid into it and allow that liquid to solidify into a glass, you will see that exactly it comes with that. So people are making very precise dimensions of glasses using this particular one single property, that the delta V is 0. and the delta V 0 comes because it is a second order transition. So, all second order transitions will have delta V being 0, and if delta V is 0, then what is the second differential? Look at what is the second differential from this. If this is the first differential of free energy versus temperature, what is the second differential? Cp by T. So, dou square G by dou T square, if I put it, it is actually Cp by T. So, it is a Cp which becomes actually discontinuous. So, the Cp of a glass is different from the Cp of the liquid at the transition temperature. If you really want to find out that what is this glass transition, what property I should measure to see that actually there is a transition that is taking place. For example, whenever you want to use thermal analysis to find out solid solid transformations, you find it very difficult. Why? Because the enthalpy that is released or absorbed is so small that you actually do not see in the cooling curve a major slope changes, whereas when a liquid to solid is taking place. For example, if I plot a cooling curve, all of you are aware of these cooling curves. For example, if I plot T versus T for an alloy, you see that it shows something like this, am I right? This is for a typical solid solution formation from a liquid, but these slope changes that you are seeing are only because of delta H differences, I mean enthalpy differences, that the moment this liquid starts forming a solid, suddenly the slope becomes shallower. Why? Because heat is evolved. When a solid forms out of a liquid, the heat is evolved, so there is an excess heat for it to be removed, as a result cooling rate becomes lower, and once the cooling rate becomes lower, the cooling curve becomes shallower, and that is why you see. And if the delta H is very very small, then you do not see a small difference here. So, a typical cooling curve, that is why a normal thermal analysis we do not use to simply find out the solid state transformation. That is why we use what is called differential thermal analysis, because we are looking at difference between a reference and a sample, where the reference does not undergo any transition at the temperature, whereas the sample is undergoing. So, and because the differences we are observing, then that is why you start seeing the peaks. So, if you do not use a DTA or a DSC, simply using a normal thermal analysis, putting a thermocouple inside the sample and seeing how this thermocouple is responding as a function of time, you will not be able to really see solid transformations, because the delta H is very small. So, similarly, if you want to see a liquid to glass transition, the only way to see is that there is a small step that you see, very very small step. Unless your DSC is very sensitive, you will not be able to see that small step. There is a small step, and that step indicates that there is. And if you can measure the Cp as a function of temperature, then you will actually see there will be a discontinuity in the Cp. Suddenly the Cp will jump, okay, from a glass to a supercooled liquid, the Cp will jump, and that jump will give you an indication that yes, there is a transition. So, a second order transition always will have a Cp change. For example, order disorder transitions, or most of the order disorder transitions are second order transitions. In fact, people some of them call them as lambda transitions, because their Cp, if you look at it, plot Cp versus temperature, you will see something like this. So, this is a disordered state, this is an ordered state. From an ordered state, when you are going to a disordered state, you suddenly see a Cp change, and that is what usually people call them as lambda transitions. So, there are a number of order disorder transitions which are second order transitions, where you will see a Cp change. Similarly, if you look at as a function of pressure, the second differential of free energy with pressure will be what? Dou square G by dou P square. What will it be? What is that parameter, if you have ever heard of it? Dou g by dou t dou p is V. So dou square g by dou p square should be basically nothing but dV by dP, am I right? Second differential of this is the first differential of this. So dV by dP is what? Rate of change of volume with pressure. What do we call that? It is called compressibility. How a phase changes its volume as a function of pressure. So the compressibility, this is a parameter which is very important for liquids, particularly when people talk about liquids. Liquid compressibility is one of the important parameters. Solids have very small compressibility, they do not change their volume much with pressure, but liquids change, and gases more importantly they change their volume to a large extent with pressure. So the dV by dP is very large for the gases and smaller quantity for liquids, and for solids it is much smaller. So wherever there is a second order transition, if you really look at the compressibility values, you will see a peak in the you will see a discontinuity in the compressibility. So that is how we can talk about second order transition. So glass transition is one such second order transition. Okay.
But if there is any change in the structure, then the compressibility won't record any rate change.
Correct, that is why is a change in the structures. Most of the times change in the structures are simply first order transitions. So that is why you do not see. In a first order transition you do not see any change. Cp also you will not see, because delta H itself there is a major change you will see. In order disorder also, if you really, if it is a second order transition and if you measure the compressibility from the ordered structure to disordered structure, you will see a small change. The small change could be small, but may not be like a liquid to glass transition, but you would see that there is a change. It depends on how sensitive your instrument is, but you would definitely see this. Theoretically, we are only saying that there is a discontinuity, we are not talking about the magnitude of the discontinuity. Okay? So that has to be remembered. So the magnitude depends on the particular system. Similarly delta H also, when we say delta H is there, or there is a discontinuity in the H when we are talking about first order transition, the discontinuity can be very very small. The delta, for example solid to solid transformation, still it is first order. The FCC to BCC transformation of pure iron is also first order transition, but delta H is very small. So it depends on how sensitive your instrument is. So we are not talking about the quantity, but we are only talking about the possibility of discontinuity. So this is how order of a transformation can be talked about, first order transition, though it may not have any practical significance, but theoretically one should understand how the transformation is taking place. Particularly physicists are very concerned about what is the order of transition, particularly whenever they talk about order disorder transitions. Many of the order disorder transitions are all second order transitions, so one has to remember. Yeah. Why glasses are brittle? Basically it is because they are very hard, their modulus is very high. So when a the question is not that, the moment you talk about, even diamond also is brittle. I do not think diamond is very ductile, because first of all the bonding itself is covalent bonding there. So once a crack nucleates, when you say material is brittle, that means the crack propagation is very very easy, isn't it? So similarly any brittle material from the Griffiths criterion, if you look at it, as long as the crack propagation becomes very easy. In a glass, whenever a crack is nucleated, there is nothing to obstruct the crack. In a normal polycrystalline material, grain boundary is an obstacle, there can be precipitates which can be an obstacle, there can be a lot of obstacles, whereas in a glass no. That is the reason why, in fact people are now trying to add a small amount of nanoparticles into glass by actually, in fact this is very interesting experiment people have done, that you think of a windshield of a car, the moment there is a crash it just shatters into pieces, isn't it? So people are now trying to put the nanoparticles into the windshield, so that whenever there is crash the windshield actually bends and goes back. So, you are making a glass into a tough material. In fact, nowadays people talk about tough glasses. There are a number of tough glasses. This tough glass concept is all coming basically because of the presence of nanoparticles. So, that means if you take a glass, crystallize it and do not crystallize it at higher temperatures, crystallize it at very close to the crystallization temperature, control the temperature and time of crystallization in such a way that very fine nanoparticles are dispersed inside the liquid, then whenever a crack is propagating, this nanoparticle can be an obstacle for it. The what is called shear band formation that occurs, every shear band gets stopped by one of these nanoparticles. That is one of the reason why many of these bulk metallic glasses per se, bulk metallic glasses may not be of great use for structural applications because they are brittle, but if you can nano crystallize them, then I can make a rod of bulk metallic glass like this very easily and then crystallize it and get nano crystals in it. So, that it is like a composite now, it is a glass nano crystal composite, and such a nano composite can be of great use. So, when I say, you see, that is I think we have been talking about it for quite some time. When you look at how glasses were first made, glass was first made by what we called it as a gun quenching technique, you remember, where we have taken a liquid, cooled it rapidly to get the liquid suppressed, liquid to crystal transformation we suppressed to get a glass. Why we had to really suppress the liquid to crystal transformation is because the crystal formation is very easy in most of the metals and alloys, because most of the metals and alloys have simple structures such as FCC, BCC, and as a result liquid to crystallize into those structures is very easy. So, to suppress that you need really very high cooling rates, so that atoms are not able to move to form that particular nucleus and the nucleus for it to grow. As a result you need very high cooling rates, whereas in a silicate glass you do not need high cooling rates. Why? Because crystal formation is more difficult there. We know that the crystals are more complicated structures. So, from that concept what people have now gone is that if I can somehow make crystallization more difficult, then I can form glass very easily. So, what they have done in these bulk metallic glasses is they have added a large number of elements. Instead of just a binary alloy, they made a 5 component or a 6 component alloy. Once you have these many elements inside this, inside the liquid, for a unit cell to form and for a nucleus of an R star size to form and grow, you see that all these 6 elements have to sit inside the unit cell. This is what we call it as a confusion principle. So, because of that the liquid for it to nucleate a solid becomes more difficult. So, as a result you can easily undercool the liquid. Earlier undercooling the liquid is more difficult because crystal tries to form at the melting point itself. So, here because crystal is not forming, you can keep on cooling the liquid without the crystal forming, so that you can bring that liquid to the glass transition temperature, so that this liquid becomes a glass. So, such glasses are called bulk metallic glasses because they are able to be cooled to a glassy state at a very slow cooling rates. For example, as slow a cooling rate as 10 to the power minus 1 Kelvin per second. So, what people have simply done is they have taken liquids of such glasses, glassy compositions, and poured into a mold of almost 3-inch thickness, and then basically cut this cross section and then looked at it in the microscope, and then they saw that throughout this cross section from the center to the surface it is all glass. It is almost similar to your hardenability parameter. When you talk about hardenability in a steels, we talk about a critical diameter. What is this critical diameter? The minimum diameter in which the center and the surface, both of them you will have martensite. Why? Because the center cooling rate is different from that of the surface cooling rate. As a result you may have a situation where the surface may give you martensite, but the center is not giving you the martensite. So, that particular diameter where you would get martensite even at the center is what we actually call it as a critical diameter. Similarly, when I pour a liquid metal into a mold like this, the surface cooling rate and the central cooling rate is different. So, if I have the central also having a cooling rate which is higher than the critical cooling rate. How do I talk about critical cooling rate in this particular case? For understanding that, I can draw a TTT diagram for a liquid to solid. The way you draw a TTT diagram for the austenite to perlite transformation, one can always draw a TTT diagram for a liquid to solid, and here what was the temperature that we put in case of austenite to perlite? That is what is called your A1 temperature. Here we will put melting point there, that is a melting point in this case. So, you will have a TTT curve like this, where I can now talk about what is called critical cooling rate. The way I talk about critical cooling rate in austenite to martensite, exactly the same way I can talk about critical cooling rate. And this critical cooling rate for a normal metal or a normal binary alloy such as a steel, let us say, is so high that I need to use a cooling rates as high as something like 10 to the power 6 Kelvin per second or 10 to the power 8 Kelvin per second, and if it is a pure metal, I may even have to use 10 to the power 12 Kelvin per second to be able to avoid the crystallization. And if I use such cooling rates, I can get a glass. In principle, for any material, as long as I have a TTT diagram generated like this for a liquid to solid transformation, I can always find out what is that cooling rate that is sufficient for me to suppress the crystal to formation, so that I can get that liquid remained as liquid until you reach a temperature here, which we called it as MS there in case of martensite transformation, and we call here as Tg. You see, the concept is exactly more or less similar. So, the moment that liquid is brought below the Tg, the liquid becomes a glass. So, this particular critical cooling rate for a pure metals is very high. Similarly, you see even in martensite also, we say when you add an alloying element, the curve shifts. Why does it shift? Because diffusion is made more difficult, the perlite formation is made more difficult. Whenever you add a chromium or any alloying elements, you see that TTT diagram shifts. The reason it shifts basically is because the diffusion is more difficult. That means the time required for the perlite to nucleate is longer, and if the time required for the perlite to nucleate is longer, it takes. Similarly, if I add more and more alloying elements into liquid, this curve shifts like that to an extent that this cooling rate is now of the order of 10 to the power minus 1 Kelvin per second in most of the bulk metallic glasses, and in silicate glasses also is almost like that. So, just 0.1 degree per second is good enough for you to be able to get a glass, and that means that you can get a glass even simply just by pouring the liquid metal into a mold, into a metallic mold, so that the center also you can get a glass. And now people call bulk metallic glasses as those where the glass forming ability is such that you get a the critical diameter of 1 millimeter. If you have a critical diameter of greater than 1 millimeter, we usually call them as bulk metallic glasses. In comparison, if you remember the earlier cases of the what is called gun quenching technique or melt spinning technique, the thicknesses were only of the order of 30 to 40 microns. The first metallic glass that people have made, Paul Douve, what was the system? Gold silicon. So, the gold silicon, the metallic glass had a thickness of the order of 30 to 40 microns. So, melt spinning technique does not really give you thicker than this. The moment it is thicker, then you lose cooling rate. The moment it is thicker, it will not have a high cooling rate. So, that is why only by reducing the thickness, that is the reason why most of the old systems where this concept of bulk metallic glass did not exist, people were forced to use high cooling rates to get a good glass, and because they were forced to use high cooling rates, they were forced to have thinner sections, because thicker sections you cannot get high cooling rate. So that is why people had only just thin films, sheets of the order of that kind of thickness, but such materials, such components are not really useful in all applications. I cannot use a thin foil for all applications, but if particularly if I want to make a structural material, so I would like to have thicker samples, and as a result now bulk metallic glasses promise you thicker sample. The glass, for example, the one which has the highest glass forming ability is a palladium nickel copper phosphorus alloy with about 20 20 20 and this is 40. This has given almost 75 millimeters thickness. That is the best glass forming alloy so far, and there are so many others with different thicknesses of the order of 30. Most of the zirconium based alloys have very high glass forming ability of 30 millimeters critical diameter. So like that we have a number of systems. So you can see the whole concept of glass forming ability comes from the same TT diagram which we are all familiar in case of steels. Okay, we will stop here. Yes, to a large extent diffusivity. The elements, that is the reason why when we take a metal, of course there are many concepts. One is diffusivity, where you tend to add metals with a higher melting point so that the diffusion is slower. You take, let us say, an aluminum, add iron to it, add titanium to it, or add vanadium to it, which are all high melting metals. Add to aluminum, the tendency is that the diffusion becomes slower. The second concept which is also important is the delta H. You should add those elements which have a large delta H, because when you stabilize the liquid, then only a glass gets stabilized. Stabilizing a liquid means the delta H of the liquid should be highly negative. We will talk about it possibly in the next class. Yes. Yeah, see this we will talk about it. They are not really need not be very high entropy. Structurally yes, their entropy is high, but configurationally their entropy need not be very high. The reason is, for example, if I take bulk metallic glass for example, with this particular composition which I have told you 40 20 20 20 obviously can have a higher entropy, but there are a number of systems where one of the element has a very large quantity, let us say 70%, remaining all elements put together are about 30. You do not expect a very high entropy, because configurational entropy, all of you know, goes to a maximum at the center of the phase diagram. So high entropy alloys are those alloys where you take equiatomic compositions. Let us say a 5 component system with 20% of each of the element, that really gives you a very high entropy. Glass ceramics are those again like nano composites, okay, where you try to crystallize a little bit and get crystals inside the glass, so that it is like a composite. So that is again basically particularly for the kind of applications that I was talking about, that where you want to make tough glasses.